welcome to our webinar/workshop on graph analytics with ArangoDB. As this is an interactive workshop, the most important information already here is on the slide. It's also been pasted in the Slack, but it's this bit.ly URL down here. ArangoDB Graph Analytics, and that will give you access first and foremost to the slides, but from the slides, actually all the exercises are linked as well. I'll also paste that, as still people are joining, I'll paste that one or a few more times into the chat. But otherwise, let's kick it off here. And because our challenge is actually this originally, the entire course was developed for like a week-long PhD course in Denmark. And this is basically now cut down version to roughly, we are aiming for 1.5 hours. So you'll see we'll try to condense the content quite a bit already in here. Next slide, please. Yes, and this is exactly why we try to focus on the first part of the overall agenda. So we'll cover a little bit like graphs, graph databases, graph analytics. If you're interested in more, I'm happy to share the full slide deck. And there's actually also an O'Reilly course which goes a little deeper into all those topics. But as said, this is our 1.5 hour workshop version, part 1. Part 2 is going to follow up with a bit more in-depth ML topics such as graph embeddings, graph neural networks, and then the ML infrastructure metadata topic, which we already got asked about in the chat a bit earlier. So me, that's Jörg. I'm the head of engineering and machine learning here at ArangoDB. In my prior life, I basically been switching back and forth between database systems and large-scale data/machine learning infrastructure. So started off with my PhD on distributed database systems, moved over to SAP, then moved to Silicon Valley to build a lot of those data and machine learning pipelines in both finance, healthcare, and various other fields. And now I'm actually quite happy at ArangoDB to combine all those passions in one role. There's just a short question in the Slack, in the chat. Did we lose audio? My audio is working fine. Chris, yours as well? Or anyone else having trouble?
Mine.
Okay.
Okay.
Chris, up to you.
Yes, my name is Chris Woodward. I'm the developer relations engineer at Arango, and that for me, it means just basically figuring out what it is that might make learning Arango easier, as well as just developing with it myself to see where it fits in. What struggles would a developer go up against? The best way to figure that out is typically by developing. And so that's what I spend a lot of my day doing, is just is working and learning Arango myself and looking into the new features and working with the community. Right now, we actually have a community project going for developing with, we're actually doing both React and Vue, and then using Arango and showing how Arango looks inside of a JavaScript full stack project. On top of that, I've worked on the Arango ML project as well. And definitely be sure, if you are new to ArangoDB, checking out the Getting Started with ArangoDB Udemy course that I did is a really good first introduction to almost everything ArangoDB has to offer that is free on Udemy. And then if you have any questions, definitely reach out to me on Slack, chris.arangodb, and I'm also on Twitter. Just happy to hear from you. And if you have questions or ideas for future tutorials or projects like that, shoot them my way.
So this workshop, it's not for us, it's actually for you. So feel free in the chat or also later reach out, your expectations, questions, feedback, ask for a break if needed. I get too involved into those topics that I forget that we might need a short break. I think it's just only 1.5 hours, so we should be fine here. But keep in mind, it's all virtual time, so we need to work together a bit to really make this work. Just reach out whether anything is off, audio, sound, questions. This is your workshop. Furthermore, this entire workshop is backed by Actually, 2 repositories. So in this one, we also have all the code, but furthermore, there's also the interactive one on the Arango side, which is linked from here, where basically the notebooks are split in between. So you can also run all the exercises later. They are backed by Jupyter Notebooks, and we'll see what that actually means in just a few slides. So you can also run that later on your free time. You can also explore the additional notebooks in here. And yeah, overall, why should you care? So why should you care about graph in general or graph-based machine learning? So a lot what we are seeing in the past, especially 2 years, is that we focus more on utilizing relationships than just data alone. And so we see that, for example, in biochemistry, we see that by special CPU or compute units for graph processing. We see that with a lot of different use cases coming up for protein detection, but also in kind of like more day-to-day tasks, which probably most of us are here for, such as fraud detection, product recommendations, and other things. And this is where we really see graph become more and more popular, and also more and more better understood across very different fields. And so what problems can we solve? So in this part, as mentioned, we'll focus on the first column here. So graph analytics. I just wanted to give a short outlook to the second part of this course. And this is basically, we'll try to answer questions from graph structure. So that can be community detections, recommendations, centrality of certain nodes, pathfinding, fraud detection. We can build permission management systems, and so on and so on. So there's already a lot to cover here. And this is what I actually always find surprising, how much we can actually solve as a graph problem, where we often don't even realize that it's a graph problem. So I think part of this workshop is actually also to just kind of showcase this graph thinking, like how can we translate a particular problem into a graph problem, or how can we detect it's actually underneath a graph problem underneath. Okay, Chris, up to you.
All right, and so what I will be doing is sort of taking over and introducing this general idea of graphs, how graphs work in ArangoDB. We'll take a look at some of just basically working with the Jupyter Notebook, and then an intro to setting up a graph in ArangoDB and running our first graph queries. And that will just get us started, and then Jörg will take over from there. So to start out, with the graph data model, the important call out is connections are first-class citizens. And basically what that means is that they're treated like anything else in your data store. So they can be returned like, for instance, in like a graph traversal, you can return an edge, you can run any filter functions over an edge, just like you would normally expect to do while doing a lookup for a query. In ArangoDB and typical of property graphs is they are made up of vertices and edges. And these are represented here in the picture. You can see the document graph, property graph. This is also how it's set up in ArangoDB, where you have an edge, where you have a vertice that has an edge that connects it to another vertice. And this is basically what makes up a graph entirely. And there's a couple of different ways that you can go about having a graph. We'll see in just a second, such as with like an RDF graph. But in the database world, there's a couple different ways that you can implement graphs. So it's either a native graph or something like built or layered on top of. With ArangoDB, because we're a multi-model database, we're actually a native multi-model database. And the reason that we make that distinction has to do with primarily performance, but then also just general usability. So because we started as wanting to have a document, key value, and graph data store all in one from the very beginning, that means that regardless of the type of query that you're running, if you're doing a graph traversal or a document lookup, you're accessing the same data store, you're using the same query language, and you're doing it as fast as any single model database. It would, of course, always be the idea. Whereas with other technologies might try and layer this, where they started out as a different type of data store and they wanted to add this functionality, but you can't really just break apart your system and then plug something else in. And so they have to sort of plug it in on top or layer it on top. And this can sometimes result in multiple query languages or just having to deal with latency from, going back and forth between the different data models, or even having to deal with data consistency and having multiple data stores. So just to call out there on what that is, we'll refer to it as native multimodal a lot of times. So it's sometimes just important to know what I'm talking about. Some characteristics of graphs would be some of the graph properties. A graph will typically have a direction. So sometimes you can have an undirected graph, a directed, or in the case of ArangoDB, it's a directed acyclical graph. So you can have edges pointing basically in either direction, but you're not going to have this looping, and the connectedness doesn't need to be guaranteed, basically. So like you can have a really, really dense graph where all the edges are connecting to all the vertices, or you can have the reverse where not every vertex is connected to every other vertex through an edge. Some other important parts of a graph, or some benefits I should say, is graph queries. That's really the whole reason you want to go through all this trouble, is what can you do with it once you have your data modeled as a graph. And so, for example, a traversal is the ability to start at a node. So for example, this U could represent a user, and you want to be able to traverse out from there. And you're going to be able to evaluate each connected node along the way for whatever property might be stored on there. So for instance, if this was like a social network, you could start with one user and look for all of their friends and friends of friends that might have some common characteristic. You can also do things like with the search example here would be starting in one place, and you go, okay, from this one place, what's the quickest way I can get over to S6? What's the shortest link I have between the two? So getting that shortest path, and other like graph algorithms such as like nearest neighbor, or just generally understanding the connectedness within a graph. Getting some of these allows for inferring basically new knowledge from the graph, and being able to do things like make recommendations just based on, who's your friend or past purchases. And even we have multiple use cases such as fraud. I don't know if we cover that one in this, but it's helpful for that as well.
Maybe just one more addition. So I often get asked this question, like, what is a more relational DB? So like Postgres, MySQL, or what is a more setup for like a graph database? And I feel as soon as it's always more about the connections, and those connections are not known up front. So for example, in relational database, you can join two tables, but it's basically like one hop, right? But in a graph databases, if you're searching for, as Chris mentioned, for example, the shortest path between two nodes, you don't know up front how many steps it's going to be. You can model that was like repetitive self joins in a relational database. But if you look at that, just writing that down in SQL, A, requires like proprietary extensions usually, and B, it also gets very ugly. C, from a query execution perspective, this is super slow. Like join optimization is one of the harder problems in relational databases. And so this is actually where graph databases shine. If you have this like multiple step hops anywhere, if it's more about the relations, and especially if you don't know the number of those steps up front.
And actually this is going to be an optional Colab. I'll go ahead and share it still. It'll be in the repo as well, but primarily wanted to look at this one just so that we can get an idea on just basically how Colab works, and take even a little bit more of a look at graphs in general. We'll be using, I'm going to go ahead and actually run all the cells, but I'll walk through it here in a sec. But we'll be using NetworkX and Matplotlib to make and draw a graph. And this is just so if you're not familiar with Jupyter Notebooks and what they're all about, you use Python in them. I think there are extensions to use other things, but primarily Python. And you can do things like install pip packages, as you see here. That's the first thing that we did. And if you wanted to run this on your own, you just click the play button there and it will run the individual cell. Or you can do like I did and run all of them, and that'll just run all the cells. And you can treat it just sort of like normal Python. There are some small caveats here and there, but for the most part, you'll have a similar experience to what you'd expect when working with Python. And here we are setting up our first graph where we're creating vertices, edges. And I'm not going to go through all of this, but I did want to just show you that as we go through and run, you can also just rerun them, and it'll just, whatever's in that cell, it's going to rerun it. So after we run that, it prints out as we told it to, the vertices and then also the actual diagram or image of the actual graph that we made.
Most importantly, you can actually also just change the code, right?
Yes.
So
yes.
This is basically just this is what we set up for you up front. But you've, in my opinion, in my experience, you really just learn if you play with that. For example, try to change the graph up there, try to add an edge, and then just see how that actually changes the different values there, the eccentricity, the degree, and other things.
Yeah, and to that point, you can change the code. We actually also have a whole repository on just interactive notebooks that cover a lot of other ArangoDB related things. And we've got it set up that if you have a cool idea for a project, you can create your own notebook using, as we'll see in a moment, we have a like sort of tutorial database environment set up that allows for these temporary databases to be created so that you can show off an idea. And I'll show you that a little bit more in a second, but it's just if you go to the ArangoDB main repository, it is called Interactive Tutorials. So definitely check that out. Yeah, you can do also all sorts of formatting with Markdown for the text cells here as well. And I mean, there's a lot of stuff even is made specifically. I know with TensorFlow, there are specific packages they've made work so that they will specifically work in Colab and in Jupyter Notebooks, because they know that it's really just that convenient. You can save the output as well. So if you're working with somebody and you want to run through this and you don't want to make them have to rerun everything, if it's a long process or something, it'll save the output and you can share the notebook that has the output. So just a lot of nice value there. And yeah, again, if you have any ideas for something or just something that you'd like to just quickly show off, we have a section where you can upload your own notebooks as well. Cool. And yeah, like we're not going to go through all of that one, but we will have one we'll go through a little bit more. Just kind of back to a bit more about ArangoDB and just being a multi-model database. This is a list of basically everything that ArangoDB currently offers. We're always adding to this. We're going to have to probably connect it to another graph of features at some point. But out of the box, the data models are document, key value, and graph. And past that, we have ArangoSearch, which is it's more than a full text index. I think it's always important to call that out. It is a similarity and a ranking engine. And so what that means is you can search more than text. For example, that project that I mentioned earlier is we're making a clone site of Airbnb, where we're going to use the new feature in ArangoSearch for GeoJSON. You can actually store and then search using various ArangoSearch functions with GeoJSON data. And we'll actually have a section later on ArangoSearch, so I won't go too much into that now. But we have iterative graph processing with Pregel. As we mentioned earlier, ArangoML is a full suite of machine learning tools, as well as a way to manage your metadata when you're doing machine learning experiments. We have kuberango, which is our Kubernetes integration, which actually ties into the next one, which is Oasis, which we use this Kubernetes integration with. So we have sort of a vested interest in keeping kuberango up to date because we want to use it ourselves. And the reason all of this sort of matters or why it might be beneficial is that you can do all of this with a single data store. And that additionally has benefits of, if you're the developer, if you have developers that are working on this, they have to learn one system rather than potentially 3 to 6 potential different systems. You can keep everything right within ArangoDB. And that just means your developer knowledge doesn't need to be fragmented across different technologies, and you can get a little bit more specialized. And this, of course, comes along with less maintenance whenever you're only dealing with one database product versus 3 or more. And the goal is always that we can do all of these as fast or faster. And typically, because there's a less separation here, it will be quite a bit faster than having to use all of the different data models spread across different technologies. And having all of this is what adds up to making an analytics use case definitely more attractive whenever you can keep it all within the same system. And this is just to show some of the sort of competitors that are in the same space. If you're familiar with like Neo4j, Amazon Neptune, TigerGraph, Cosmos, these are all different technologies that we kind of benchmark ourselves against to be as fast or faster. I mean, we know that if you're using a single model database, if you're going to use a multi-model database like ArangoDB, it needs to be all win. And so that's always what we're aiming for. Okay, so AQL is our query language, and we'll see a little bit more of this in the notebook that we cover, but just if you're not familiar with it, it's the ArangoDB query language, and we needed to make this language up because we're a multi-model database, and that's not really a thing, especially not a native multi-model database. So we needed a query language that had the ability to do graph traversals, and in the same query language be able to do a normal document lookup or key value lookup and nest all of these at the same time. So for example, this query that we're showing here starts out with doing a basic company name lookup, and then we do actually a graph traversal. And then in the results that we're actually returning, we do another lookup based on the findings of that graph traversal. So this sort of joining and traversing is really common in AQL. And the goal of the query language was to be SQL-like, but to me, I mean, it's way more human readable than SQL. And additional benefit of learning AQL is that it does work with all of the various drivers that we have. So Java, JavaScript, the Python is actually our community driver. We have a PHP, Go driver, all of that. You can use the query language with it. It's the same query across all of them. So, and like I said, we'll see a bit more on that, what's going on there in a second. And ArangoSearch. So the main point of this slide is just to also say, like, just driving that point home. With AQL, it is always the goal that you can do whatever you need to do in one query, or you should be able to combine the use of multiple data models in a single query. That is you always want to make sure you can actually have the benefit of a multi-model database. So for this example, we're doing a description search. We're using our IMDb movie data set here, and this is searching the description. And once we have that description, doing a traversal out from there. So the way this one works is you'll have a node that is a movie, and then it'll have connected edges. And those edges will say things like acted in, directed, writer for, and then the node that it connects to is that person. And so in this case, we wanted to find the director. So we would traverse out from, or you could actually kind of do it either way, but in this one, we're saying inbound. So we'd look for an edge that's connecting into the movie, and it would say directed. So there would be a person that directed it. We can return the director and then the movie. And furthermore, all of these are sorted by a ranking value. We have access to the BM25 and TF-IDF ranking algorithms, and that makes it so that the results you're getting are actually relevant and sorted in a valuable way.
So maybe just to come back to that point, I think one of the key value propositions is that you can actually do that from one query language and from within one system. So I built in my past, or I've seen so many different systems where you actually drop in like Elasticsearch next to a graph database, next to a document database. And then you typically have to build that query layer on top, connecting all of that. In practice, still building another database system, keeping everything coherent and consistent. And I think this is one of the key parts, is this is all happening from one query language and from within one system, so there are no duplicates of the data.
Exactly. Yeah, and I think that's something that if once you get started with it, you realize just how natural it is. It's like you make life harder if you need to separate these queries. And I saw real quick a question about the Udemy course. So just look that up.
I'm already pasting it.
I beat you to it.
So,
yeah. There's that. And yeah, so then also the rest of
the short answers, there are a lot of free training materials. ArangoDB is also an open core model, so you can use all of that like an open source. There are some enterprise features if you really want to scale it out to very large use cases. But this is also why we have a lot of contributions to the training material. There are a number of different courses online. And feel free to also suggest if you're missing anything in terms of material. The other question here for setting of results, yeah, like this is kind of like Elasticsearch there.
Yeah, and even furthermore, with ArangoSearch, we've added recently a suite of tools for fuzzy search functionalities. So using Levenstein and Ingram matching functions, and like I already mentioned before, the GeoJSON. The coming GeoJSON functions in the next version. There's a lot that we can do, hopefully, to be a good substitute for fuzzy or Elastic, but it's similar in that way. Okay, and as I kind of mentioned, was the comparison to like an RDF triple store. We put these on here as two of the main graph storage models. We've gone over sort of the property graph model, node, edge, and vertex, whereas with an RDF triple store, this is going to contain documents that are like turtle files or in triples. The main theme being is that they have statements that contain triples, which is this subject, predicate, and object. And so it can be thought of as basically a single line or a single like statement that makes up a graph or a portion of the graph, where there aren't this idea of like edge documents like we have with the property graph that might have additional properties on there. They're all sort of single ideas connecting each other. This is a way bigger topic that I'm probably giving it credit for, but these two graph models have sort of been separate directions you could go. And the reason that this slide is here is that we understand the importance of RDF, and a benefit of RDF is that it's used in the semantic web with like things like Wikidata or DBpedia, and it is used to allow to be machine readable. That's its whole purpose, so that machines are able to read it and infer new information out of it. Probably the most common use case for something like a knowledge graph is going to be something like Siri or the Google Assistant, where they search large amounts of data to just infer maybe explicit data that wasn't explicitly there. But if you ask it an unrelated question, you can actually get some information back out of it. That uses a query language Sparkle, whereas typically with property graphs, you're going to have a proprietary language of sorts, so AQL, Cipher, and those. So something that is sort of interesting understanding that is that there's this upcoming idea of RDF star, which does aim to bridge this world between property graph and RDF. The value of RDF is always going to be there. It deals with massive amounts of data, of linked data, and but having the ability to put it into a property graph to make it a bit more human readable, a bit more queryable by humans in general, and then having all the other benefits that you might get with a database like ArangoDB, where we have all of these features that we've talked about that we can now apply to this data, would be great. And RDF star allows for nesting these statements. So here's this this subject predicate object statement I was talking about, where normally just this 3 right here would be considered one. But with this RDF star implementation, this would be considered like a nested attribute, and then this would be the predicate object. So your individual statements and documents get a little bit more complex and a little bit more descriptive, and that gets them a little bit closer to a property graph. And so there's already a lot of efforts started on this. This is a spec that's still in draft and still being worked on. So very early, but it is just something interesting that I'm actually personally looking into. And so if you are interested in something like this and seeing the connections happening here between a property graph and a triple store, or primarily just RDF documents in general, RDF graphs, definitely reach out. Let me share. I'm actually going to share this one just because it has basically all the links that you would need if you'd like to learn more. That's a really good starting spot. And that actually might be a good spot to stop if there are questions. Any important questions there? I know I kind of blew through that, so maybe.
So I try. Let's try to answer some questions. So graph traversal filtering out together with ArangoSearch. Please ping us on Slack, because yeah, you can filter up front. It just might have some performance implications. So let's just briefly talk about how to best model that query. Next thing are .NET developers. There's an .NET driver and community integrations. We are not discriminating against anyone using .NET here. Also, I'm happy to paste the link here, how to do things in .NET. Just for this tutorial and for our notebooks, .NET, there are some projects who bring that up in Jupyter Notebooks, just it's much simpler to do that in Python. The reason, so kind of this bridging between the two worlds, or why ArangoDB isn't built on top of RDF, but property graph. So Chris, can you go back one slide just for 1 sec? So basically, those are coming from two different directions. Like property graph is kind of this practical approach. How can we build things? Whereas the RDF triple stores are more built for like scientific reasoning or large scale knowledge sharing. So just if you talk to a lot of people, or if you just Google this debate, property graph versus RDF, you'll see that a lot of people are pretty strict on one side or the other. I actually feel that we can bridge this gap. It's not RDF versus property graph, but internally we actually represent graphs differently than RDF for performance reasons and also usability, because just imagine like here in the schema you have just adding like a birthday to Paul Schuster is gonna add a lot more facts to the RDF graph, which often makes it like very hard to express or to evolve in a company settings. But feel free to reach out. This is like a very long debate, and I feel like the best of both worlds is actually in the middle.
Yeah, I think to add on to that, like you were saying, with adding a birth date to Paul would mean adding the equivalent of not exactly the equivalent, but it's almost like adding 3 more documents in a way, where you have to have one that says Paul, one that says age, and one that says the literal value, whatever his age is. Whereas in a property graph, you just add the age and value property to a document. So that's not saying one is better than the other, just that's the sort of like difference. And I could see that with the performance implication sides of it.
But very, very good questions. Keep on asking.
Yes. Okay, plan to enable property graph. I don't know if we're saying we would plan to enable property graph to triple store, but we're looking at it with this idea of an RDF star for at least tools to help with that.
Yeah,
and there are already a number of tools that exist.
Yeah.
RDF.
Okay.
Agreed, William. Okay. Is there any benchmark comparison with dgraph?
I don't think we have shared any, but yeah, there's some data. I need to look. I don't think it's public.
Okay. Awesome, thank you. Okay, and just one sec before we move on, we actually have ones in the Q&A as well. I think we already, the data scaling one.
I'll try to answer those. Just then you can continue with the next one.
Okay. Okay. So actually, we are now on to the queries portion. This is going to be the notebook. I'm going to go ahead and share this as well. This will be a good one to follow along with. I'll try and give you guys time to make sure everything's going. Give it just a minute here for everyone to get that pulled up. And so I am actually going to go ahead and run all of these just so we're not waiting on me to do it all. The first portion of it is we're actually pulling in some data from a repo. It's just some of the data that we'll use throughout this. I don't think we actually have a data set, but we have a small Python utility for connecting to Oasis. And so this is creating this tutorial database that I was talking about, and it will return the credentials you need to log in. If you want to keep using this after this is up and you have your own Oasis account, or you want to sign up for a free trial with Oasis, you can get a free 14-day trial. You can actually create a test database there. It's in the example section once you have a deployment up. And you can come in and paste those credentials in place of this here. So you just go to cloud.arangodb.com, sign in, and then in the examples, there's an option to create a test database. And you can use that for all of these notebooks. You can just use those credentials here. Okay, so we've got ours. And this is, again, is for a different one. I don't think we're going to cover that in this, but just talking more about that RDF side of things. Okay, so the first thing we're doing here is actually setting up the graph. And using this PyArango driver, we set up our classes for our collections and the actual graph itself. And then we actually create those collections. Once that's created, we create a graph. And then using that graph, we start adding our vertexes and edges, referred to here in the driver as a link. And so all we're doing is adding a number of people here that we will show like sort of a family relation for. And since this one's already done, I did want to show you that if you run that tutorial notebook, it'll give you the link to go to, just tutorials.arangodb.cloud with this port. And then it'll actually give you login credentials. You should use your own, just in case you're wondering why I'm not giving you time to worry about finding them. Once you get logged in, it'll be a fully functional ArangoDB database. And for instance, we maybe didn't add them yet. Right, no? Did we not run this? Thought I ran it, but maybe I didn't.
Seems to have run. There are numbers up there.
Oh, there we go. Okay, so just wanted to show you real quick, basically what should be generated is you'll have the family members connected on a graph. You can do some various options. I'll show you a bit better example for the next one here, which is our train network. This is a graph showing the like basically a train network and travel times between each station. And some of the examples we'll look at is basically time that it takes to get from one station to another, shortest destinations to others. And let's go ahead and set this up so I can show you a little bit more there. Seems like it didn't add all of them. Just rerun them from here. Okay. So similar thing here. We've set up our classes for our collections and our graph, which we're naming Rail Network. And with ArangoDB, the thing that you're always going to need to do for a graph to work is have these edge definitions, so these edge documents. And I want to take a quick look at those now. For instance, for this one, we're dealing with the connections in our train network. And these have a _from and _to field. And this is the general structure of graphs in ArangoDB, is that you have these edge documents, which are full-fledged documents. As you can see, you can store properties just like any other normal document, with the additional criteria of they have to have these _from and _to fields, and these reference documents in our vertices, so in our cities collection. And actually, I can click on this. Oh, what's happening here? Well, I don't know if others are maybe using this one, but looks like it's having issues there. One sec.
Are you overloading the cluster?
I don't think so. It just looks like, oh, well, let's see. Let me try and run this again. Oh, I know what happened. The very last one is that it drops all collections. So maybe I'll just comment that out. Just that is there just as a cleanup step that did not need to happen. Okay, there we go. That makes more sense. Okay, so now I'm going to let those get added, and it should run all the way through without deleting all my data again.
I'm trying to answer all the queries here. And if I answer like very briefly, I'm sorry, there are just a lot of questions. So don't take that personal and just hit us up on Slack for longer answers later.
Yes, yeah, and if you were running this on your own as well, make sure you go ahead. If you run all cells, make sure you have this last one commented out as well. You're going to have the same issue I had. So, but once you've done that, you should be able to come here. There's our collections. I started it from the train network one, so we only have that one there now. But now we have our rail network graph, which actually, let me go back to the point I was showing before, which is our edge documents, linked to cities documents, and our cities, in this case, are pretty empty because they're just supposed to represent a node on the train network. And here is that train network in our graph viewer. And I want to make these a little more descriptive. So something you can do with our graph viewer is change the labels for their different graphs. So I believe it is travel time. Yes, okay. And oh yeah, if you'll notice, the numbers look a little weird here. And that's because, as you'd expect with this train network, you have routes going from London to York and from York back to London. So they'll kind of overlap. But something you can do is just change the style of the line. So now we can see all of the connections, their times, which are representing travel times. And I just hit this button up here to load the full graph. And so now you can see we have graphs for in Europe. We actually have a Canadian graph here. So just a couple different ways to explore the data. Yeah.
To answer one of the questions in the chat, so there's pip, and there are actually 2 Python drivers. This is one of the advantages / disadvantage of being very open source. So our community actually provided 2 Python drivers, both having different advantages. This is why in some notebooks we use one and in some the other. So just import both for now. Of course, the Oasis toolkit actually depends on both because it can just generate both connections. So just hit both for now, and feel free to submit a change to aces.py to just work with one or the other a bit more optimized.
And I saw someone mentioning something about persisting the settings. I don't believe, I mean, there's a save, but I think that's just saving for this session, if I remember right. So, so yeah, you can save it for this session, but it does change if you were to like close the window and come back. Okay, actually, I'm going to close this one. We're not in that anymore. Okay, so now we've got our graph set up, and we've got our cities and our connections. And what we've done here was whenever we made our connections, these were those edge documents. We gave it our from, our to, and then their respective weight values. So, and as we'll see in just a second, oh yeah, we gave that here. I want to show you the actual query that cares about those weight values. Okay, so I do want to walk through this query just sort of line by line. I'll try and not spend too much time on each section, but this first one where it says with and then cities, this was useful, and I think we're still saying to do it for like cluster deployments, where you call out the specific collections that you're going to use in the deployment. Single server, this isn't necessary, and this is just a way to make basically the query aware of the collections it'll need. The next line is for. You start out almost every query, AQL query, with this for keyword. And the unique part of that is the vertex, edge, and path. This is unique for graphs. And so what we're saying is we're going to have access to a vertex variable, which are going to be the nodes that we traverse, the edge variable, which are the edges connecting them, or the path, which consists of the full path of nodes and edges that we made for that traversal that matched our criteria. So here we're saying we want to do a depth of 5. So looking back at our example, basically we're saying if we started from here, go 1, 2, 3, 4, 5 nodes out or in, depending on the direction that you give. And this in indicates that we're about to define the direction. So in this case, we're saying we're starting from London, and then we are going to travel outbound, and we're just looking for paths coming out from London that when they're added up together, because we're looking at their edges and the travel time value, which is what we looked at before. So these 1.8 here and 3.5, we're saying add those up and they should be less than 5. We're just looking for a path that leaves London, that wherever I'm going, I'm going to get there in less than 5 hours. And then we're returning that and just doing a little bit of manipulation here for displaying the results. So, and that's what we get here is we can say we can start in London and go to Birmingham in less than 5 hours, and London to Birmingham to Carlisle, and so on. And if we look here, we can see that that's true. So we start at London to Birmingham, and London, Birmingham, Carlisle. Those all add up to be less than 5. And you'll see actually there is an example of here, London, Birmingham, back to London, because that is a valid path. So round trip is still less than 5. Okay. And I'll maybe give it a second there. Any questions so far? Everyone able to run the notebook and everything properly? We're looking okay. And okay, so that was just an example of a basic graph traversal where we have our variables, we say what direction we're going, we have our start vertex, and then we have the graph. So something that you don't always have to do is use this graph keyword. There's this idea of a named graph, which is our rail network, which says we have these predefined vertexes and edges and everything that would be involved in our graph, or we have what's called an anonymous graph, which is sort of a benefit of using something like ArangoDB, where you can just have edge collections and vertices that exist separately. so that you could define multiple vertex collections to use here or just one. So in our case, we could just declare the connections collection here, and we would get the same results because we're saying start from this vertex and then use these edges to traverse a graph, and we don't need to know basically what those edges do because it'll still perform the traversal on them because they're connecting to valid nodes. Okay, next up is the shortest path. So this is k shortest paths. This will typically return a number of paths that qualify with our criteria. So you have k shortest paths or just shortest path, which is just going to return 1. We actually limit it to 1 here, so it's sort of doing the same thing as that. And what we are looking for, we're just saying return our path, we're just saying return our path, and we're going outbound, k shortest paths, starting from Aberdeen to London. So we're saying we want the shortest path from Aberdeen to London. And again, using our graph keyword and our rail network graph. And as you see, we returned the vertices of that path. So that's our output here, the cities involved from going from Aberdeen to London, and then the travel time that it took for each individual stop, and then the sum of those travel times. So this whole trip from going from Aberdeen to London, 8.3 hours, or whatever unit of time you want for that. This is a little bit of an extension on that one. Instead, we're returning multiple paths, but this time we're including this options value. So this is saying when you're evaluating the paths that we have, we can define a weight attribute, which is what we are basically already using, which is our travel time. But we're saying if there is a stop that doesn't have this travel time, we want to give it a default weight of 100. And the reason we're doing 100 is we're saying, well, because there's no travel time attribute, we can't really take it into account. We don't want to give it the default of 1, which would make it seem like it's a really close destination. So we're just going to give it this high value. And if it still ends up being a really awesome path for some reason from there, then great, put it in our results. Otherwise, we just need it. It's basically saying it needs almost needs to be removed from the results or have a really low score, just because there's a lot of uncertainty there. And that's the same thing where we get now some paths, and it breaks out the travel times for each of our potential paths that we could take. And yeah, so there is the quick intro there to graphs, and I think that is actually where I will pass it back over to Jörg.
Cool. Can I actually take over screen sharing in this case? Because then I don't have to ask you to move over the slides.
Do you want to just me stop and then you start?
Yeah, that would be perfect. All right, and here we continue. As said, also feel free to just follow along with the slides. But now let's actually dive into the second aspect of our webinar title, graph analytics. And so actually, when I wanted to Google like a good definition of graph analytics, it's super easy to find, I think, decent definitions of analytics in general, like computational analysis of data or statistics for discovery, interpretation, communication of meaningful patterns in data. So I would actually translate graph analytics to basically do the same, but like specifically for graph structured data. But it was just like much harder to actually find a good description on that. And I think it's just similar to what we mentioned earlier on databases in general, that as soon as it really matters about the relationships between different entities, imagine like a social network graph, imagine like protein folding or drug discovery, where it's a lot about the relationship between different ingredients. If you have like an IoT high-level graph, fraud detection, where you just want to link a lot of different entities, this is when we actually talk about graph analytics. So basically just in that definition of analytics, just say like graph data or graph statistics. Just to kind of like reach out, if you're in general interested in analytics or machine learning, I can really just recommend like Fast AI. They have a lot of free courses, and they're also not just focused on the newest trend, this deep neural networks, but actually cover a large range of other machine learning and analytics systems as well. So if you really want like an in-depth course, this is one I can fully recommend. Why should you actually think about graph, or what changes if you model something as a graph? So here, for example, we have similar, Chris had said a bit on earlier on as well, the IMDb graph, where we have like different movies. They belong to a different, they belong to a genre. They kind of like cast members. And so for us as humans, it's actually much easier if we look at things as a graph. So here on the left, we have the same information represented in like a tabular format, but now just try to figure out like a particular actor in which movies he has played. You actually have to go through the entire cast column, potentially breaks it apart, and then figure out all the movies. So it's really just this relational structure is optimized for this one lookup on a key column, but it becomes much harder if you have to break up like a cast. So what's specific about cast is it's actually like an end-to-end relationship. You could, of course, also just model that in a different table. So basically, next to that, you would have your cast table. But again, then you end up having like a number of different joints in there, which already makes it much harder for a human to just interpret that on like one look. Also, this is why we see this trend of like, especially around knowledge graphs and machine learning really picking up over the last year. Also on the first slide where I had this motivating year of graph 21, this is a really interesting blog post if you're more interested in the value of graph towards analytics or recent trends of graph and machine learning. But now let's actually just talk about some things we can do on graphs or graph algorithms. And so typically, if I wanted to group them, I would say there are like some fitting into the search and traversal category, finding a specific edge like breadth first search, depth first search, which probably many of us have coded like back in our, sometime in our education or some coding interview, code depth first search or breadth first search. Pathfinding, and this is what Chris already showed, how can we get from A to B given a number of constraints? So for example, shortest travel time, which we can compute based on different measures. And that might also encode like some other constraints that I don't want to cross like a particular city because ex-boyfriend as ex-girlfriend is living there, or something like that. Centrality, and this I find very interesting in graphs. It's about like what are important nodes in a graph, and now of course it depends a lot on what we mean by important, and we'll see that this changes the notion of what we define as a central node in a graph. But if you're talking about like a social network graph, for example Twitter, you can imagine you try to find the influencers which reach a lot of other people in that network. Next, and I believe that was also a question on in the chat already, is like cycle detection. So deadlock detection or network analysis also has a lot of different usage. So for example, as mentioned, like deadlock detection, even in databases system, transaction A depends on transaction B, depends on transaction C, depends on transaction A again, and we have a full loop. So once we detect the cycle, we actually know that there's a deadlock there. And last here is community detection. Basically the question, are there any particular subgroups being available which we can distinguish from others? All right, let's go through and let's actually take a look at shortest path first. So I always included like links down here where you can actually look at what that means. But for shortest path, there are a different number of different algorithms. So for example, Dijkstra, Bellman Ford are probably the best known ones. And then, as Chris already showed, there are different algorithms optimized for k shortest paths. If we don't just want like z shortest path, but a number of shortest paths, and then also single source shortest paths. Basically, single source shortest paths is like, hey, from one, what are all the shortest paths to all other nodes in my network? And of course, you could now just run the shortest path algorithms for all target nodes, but as you can imagine, there are more efficient algorithms for that. And there's even like a yet better algorithm if you really want the shortest path between like all pairs, from 1 to 2, 2 to 4, basically from any two cities you want to figure out the shortest path and then just look that up. Dijkstra basically works very, very simple. You always just kind of try to follow the shortest path until you end up like with a cycle. And by that, you always take kind of like the next step, which is kind of like 2 here is the shortest, and 6 is the next cheapest path, and so on until we actually find our node here. And this is also a very easy algorithm to implement. Minimal spanning tree is another very useful thing to actually do a lot of different things. So a minimal spanning tree is basically the tree, the subset of edges connecting all nodes which are in general in this connected component, and basically dropping all others. So basically, what is the cheapest path of connecting all nodes without inducing any cycles? Because any cycle means that we can easily delete one node. Because there's a cycle, there are 2 ways to reach one node, so we can always delete one edge. And again, for that, there exists a number of different applications. So for example, one interesting one is image segmentation. Others is like networking and broadcasting. Imagine you're in a network and you try to reach everyone. This can also be just in a physical network where you try to broadcast a message. You try to find out the minimal cost to actually reach all nodes in that network. There are, again, different algorithms. So Preem's algorithms or Kruskal's algorithms, they're actually very similar, but I would leave it up to you to actually follow up on the links shown here, just in terms of time being available. But here, Preem's algorithms, as mentioned, it's actually very simple because we are always adding kind of like the shortest edge, and then basically built up our graph. And if you look at Kruskal's algorithm next to it, it's actually very similar in like a congruent form. So I would actually recommend, if you have the time, look at an example with Preem's and Kruskal's algorithms next to each other. And as said, it's actually here on the slides as well. So we touched upon cycle detection. So cycles, this is in like directed graphs. So I need to have direction. I can also do that in undirected graphs, but it's usually I want to look at that in a directed setup. So here, for example, we have a cycle as we have a path where we can end up back at 1. And this is, as for example, for deadlock detection, or also in general network analytics, it's a very important tool. And again, there are different algorithms. You can actually use just depth first search and see whether you end up identifying something you've seen before. Then there is like Floyd's algorithm, which is also called like tortoise and hare algorithm. So basically you move through a graph and you have like 2 chasing pointers. One is always like moving 2 steps ahead. One is always moving 1. And as soon as if they ever end up on like the same node, you know that there's a cycle. So I think that's it for cycle detection. Again, there are more links here. Community detection. This is basically how we try to identify like subsets. So for example, here we have kind of like different sub-communities where you can also see like different roles. So for example, here, this is a very densely connected component and this cycle here. Then here, this 4 and 5, they actually have the function of combining those 2 sub-communities. And then again, here on the right, we have another very densely connected subcomponent. And so again, there are different ways in identifying that. One is triangle count. Others algorithms for identifying strongly connected component, a number of algorithms here. And one thing which is becoming rather popular is simply just a label propagation, where you can imagine like having like a little message being passed on between different nodes, and that kind of like labels different subgroups. So for example, one is passing on its label red in this case to all the neighboring nodes, and then at the end you kind of take a majority decision which color your node has. And those again have a number of different meanings for social networks. You try to identify subgroups where you actually might recommend people to join. Also for clustering, if you try to how should you shard this graph between different nodes? If you have a very large graph which doesn't fit on a single node, how can you actually split that up between different entities? There also community detection is important, because you try to identify communities which have most interactions with each other. Topological sort. How many of you have actually used makefiles? So in makefiles, in the end, you need to identify like a specific order of steps being taken out there. And this is an example of topological sort. So topological sort basically means here, if we have an edge from 1 to 2, this means that 1 has to occur / be sorted before 2. Similar like with 1 to 3, 1 has to happen before 3, but we don't know anything about the interaction between 2 and 3 about that order. So it's just a partial order there. But we know that both 2 and 3 have to be sorted before 5, because they both have edges going here to 5. So this most often happens in DAGs, so directed acyclic graphs. And the topological sort is not necessarily unique. As we can already see here, we have different ways in which we could, for example, sort 2 and 3, and then also down here, we have different options for our topological sort. And the applications here are, for example, makefiles or any other dependence system where I have to figure out like task A has to occur from task B, and I have to find like one valid order of this dependency graph here on the right. Maximum flow, this applies to weighted graphs. So if I have a graph here, so this is a second number, which tell me like how much capacity do I have, then often a question is how much capacity can I channel through from S to T? And just look at this. This actually might mean I channel like some capacity up here, some here, and then around here. So basically the question is, how much can I channel through this entire network given the directed graph here? And there's even like, there's a lot of different algorithms for that. So if you just look at the Wikipedia article, just look here, how many different algorithms we can actually apply for that. Okay, I need to move my here. Next, we come to this topic of centrality, and recall this actually means we want to identify important nodes in a graph. And important, unfortunately, but interestingly, can have different meanings. So if we, for example, look at the degree and centrality, degree, we had that in the property of different graphs, means like how many in and outgoing edges does a particular node have. And so basically the most central nodes is the one having like most in and outgoing connections. So according to this, this would be the most central node because it's connected to most other nodes in this graph. Closeness centrality, this is the average closeness to all the nodes. So how many steps do I need to reach all other nodes on average? And there we actually have a number of different candidates here marked in green, which would have the overall, the average to like all other nodes being equal. Betweenness centrality, this is basically how how much of a failure point or how much of a connecting factor that is. So if you, for example, have a social network, you can identify that there are two very large sub-communities, and then there's one person in the middle connecting them. So this would, for example, be an important node in terms of like connecting different sub-communities. And for example, also here, if this node would go, this graph would actually fall into two subcomponents, the one here on the right and the other one here. So this is like a betweenness, important betweenness central node. And how you can actually compute it is how often is this node on the shortest path. So you compute the all pair shortest path, so shortest path between all the different nodes, and then how often does a particular node show up on the shortest path. And last, we actually have here PageRank for that, and we'll touch upon PageRank a bit later. So PageRank was kind of the original algorithm, which kind of like Google became famous with, and there are also a lot of other applications. So we actually have a few more slides coming up for that later. I will briefly look into the Q&A. Chris, were there any important questions to be answered right now? You're muted.
Oh, we just got asked one. Have there been customers who have used community detection with Arango graphs which have launched in alpha/beta trials?
We have a number of users and customers using community detection, yeah.
I was trying to, do you know of any ones that we have a white paper for? I think we do, but couldn't think of
I would have to look up our white papers, but yeah, as said, in doubt, just reach out via Slack and happy to provide more answers.
Yep.
Okay. Then just continue. As we already seen this NetworkX, this is what Chris showed briefly on the first notebook. It's a really cool networks analysis tool in Python, so it's pretty powerful. I would call it like the Swiss Army knife for graph analytics in Python. Obviously, this only scales to like very small graphs, but it's really cool if you want to do research. You first want to figure out how to solve a particular problem on a smaller subset, and then you actually bring that over into ArangoDB for the really at scale execution of things. And let's just go back here. And yeah, I just see that question. Are we sharing the recording? Yes, we're sharing the recording later on. So again, this is the notebook Chris actually showed earlier. And I typically, what I do, I actually run the cells by hand. But the first part we're actually familiar with, creating like our first graph, showing some graph properties here. But then NetworkX actually also has a lot of algorithms inbuilt. So for example, here, we can do our graph traversals. So we can do a depth first graph traversal, NetworkX. So typically it's abbreviated as NX, depth first search and depth first search enumeration of the edges, then a breadth first search. And it also has a number of different generators available. So for example, here generating a complete graph of size 5. And then basically we have algorithms for all the different algorithms we just discussed here. And they're even more available. So for example, if you miss anything, I can just recommend you to browse through this. It will take a while, but as mentioned, it's a very powerful tool for graph analytics at small scale. So if you're doing your exploratory analysis. So what I would recommend, I would just give you like a few minutes, as we are also a bit short on time. I would just give you a few minutes to play through that and ask questions. In the meantime, we'll try to answer some more questions and then actually continue with the presentation part. Again, I can also once more paste the link in the chat. But keep in mind, it's also available in the slides. So if you're just clicking through the slides, feel free to click through as well. There's this one question about how loops can be detected. We actually have an example for that in the fraud detection part coming up. Okay. As said, I kind of feel sorry to rush you a bit, but the exercises will still be there. And as we're aiming for 1.5 hours, I would just continue a bit, but still feel free to just ask questions up front. The notebooks are going to stay there. You can run them whenever you like later as well. And we are also available on Slack for answers. So now let's actually combine all of that and see where graph analytics with a graph database, or ArangoDB in particular, comes in handy. So fraud detection. So for example, you might have read about those Panama papers where they figured out all this people laundering money and trying to avoid taxes, where they looked at like a large bunch of data, but they could actually identify like those closed loops. This is where the question came from, or the answer will be in how to detect closed loops. We also see that it's useful in permission management, because you can actually see permissions in large enterprises also as a graph, Internet of Things as a bill of material, representation learning. So we can actually do a lot in terms of graph analytics. And as promised, we'll try to talk a little bit in how we can actually see something as a graph problem. And this is why I would like to start here with the example of collaborative filtering. So you all have probably seen that on Amazon or on iTunes, Netflix. Customers who have bought this also bought this, or people who like this movie also like that movie. And again, this can actually be viewed as a graph problem. So if we want to answer the question, which movie should I watch next, given probably most of us are still in like self-isolation, lockdown scenarios, it's a valid question to ask. So how can we view that as a graph problem? So IMDb actually has a lot of information available. And here we have information that a particular user rates a particular movie. And this is basically a graph, user, the edge is the rating, and then we have the movie here on the other hand. And so to find movies I personally like, we can kind of ask ourselves the question, I want to find highly rated movies by people who also like movies I rated highly. So basically, I know Chris, and Chris actually likes similar movies as I do because he rated the same movies I rated very highly. And now I want to figure out like which other movies Chris actually liked, and so it might be worth watching for me. So how can we do that in terms of a graph lookup? So first, I need to find out movies I rated very highly. So I take like as a particular vertex in our graph, I take like the representation of my user, and I find all the movies I rated with 5 stars, highest rating. Then I actually go back and I find all the other users who rated that same movie with 5 stars, because I would assume that they actually have a similar taste than I do. And then from this set of users, we actually find out like all other movies they rated very highly with 5 stars, because those are potential candidates we might want to watch as well. And again, we have a lab for that. I need to move the Zoom stuff down here. But again, this is setting up one of those temporary databases. Down here, and I will just quickly run through. So the data set from IMDb, it actually comes in CSV format, and this is I like that because it's actually like a real world use case. So often in real world, you will have like CSV data and have to import that in a graph database. So first thing, we create our graph here. And then what we actually do is we go through our CSV file and we basically insert that into our graph collection. This will take a while because those are actually quite kind of like big, big graphs. Here we just look at the first 3 rows, but this is why this will run a while. And then we do exactly what we described earlier. We try to do that step by step. So in the first part, we tried to find like my ratings. So the movies I rated with 5 stars, simple like one edge graph traversal. And then we go back and we try to find users who actually gave similar ratings to those movies. And then in the last step, we can actually identify new movies here. So in terms of time, I will hit, has that run? I think they, oh yeah, this already has run. Yeah, this has run as well. This is why it's here. We find the movies I liked quite a lot. Is that actually true, as I just picked like a random user? Yeah, some of them I could actually watch. Next, we identify
Star Trek on there at least. That's those good ones.
Yeah. Next is actually users which are similar. Oh, and just consider I put like a limit clause in here to just limit the number of outputs, because otherwise there are actually a lot of ratings in there. So if you would do that in a production scenario, you would obviously drop the limit here. And then we can actually identify movies which I might want to watch. Raiders of the Lost Ark, yeah, it's actually not too bad. Recommendations here. And so with that, I think we already implemented like a common problem of like product recommendations as a graph problem, which is, as I would call it, is kind of like this graph thinking, how can you model something as a graph problem? Feel free to run that.
There is a question in chat. Supplement the query with other sources like DocumentDB. I'm not sure what that meant by adding. You mean adding other collections to the graph as well? Or?
Yeah, you can add other document or external data sources. So, for example, you could use a DBpedia link to that to get more information about users, but then you just have to import that other graph data. And the next question, what about example for product recommendation? So I think we just did that for movies. If you basically have a similar system for products, like which products you like, which products you would recommend, then typically you would combine that with like some other attributes in usually like a hierarchy for which category is in, because you're not just looking for any product you might like, but typically you're looking for a product in like a specific area. And so if there you can then combine it, for example, with the ArangoSearch full text search Chris mentioned earlier.
We also have an Oasis guide that uses the Instacart dataset for an e-commerce example. So that can kind of get you on your way there if you wanted to check that out.
Okay. Fraud detection. How much time do we actually have? Oh, left. Again, for fraud detection in like a banking network, if we just see a simplified version of like that, we have like different banks. Banks can have branches, and branch can have customers. There are different accounts, and customers can be account holders. Like in some cases, this could even be like multiple, if it's like a shared account between 2 people. And then between different accounts, we have transactions. So transferring money from one account to another. And this is, I think in terms of time, I'll just walk you through what will happen here, but we'll try to identify different kinds of fraud in our network. So first, the different techniques is like find long loops. And this again is an answer like, how can I find those closed loops? So fraud rings. And that basically means there have been people trying to go from account A to account B to account C back to account A with their transactions to just kind of diverge that train of money. And that can actually, like in the end, this is the kind of more interesting case, it's being split out, like account A originally has like 100,000 and 50,000 of that go to account A, 50,000 to account B, and then basically through like long loops of aggregation and disaggregation, it ends up at like account C, for example. These are basically the queries for that. And for example, here you can already see if you're looking for a particular account, this closed loop search is pretty easy because we actually have we start from like a particular account, and then we filter in the end on the edges to like the end account as well. So it's actually also a very efficient operation. Next, we can also do that here with the suspicious account, and this is basically going through all accounts and doing something similar up here. So basically, again, filtering and trying to search for loops in our network. And so just to keep in mind, Chris showed that a bit earlier, this is actually on the edge collections directly. So it's a very efficient way of looking through there. And then just down here, we actually have this bit more complicated pattern of disaggregation and reaggregation, but still, this is actually very readable because if it's just going to take a bit longer to run on this entire network. So, all right, so this was the fraud example. Again, up for you to run. And next, let's come up to PageRank, because we wanted to talk a little bit about PageRank. PageRank, again, is a way to identify like centrality. We try to identify important nodes. And so in the Google case, this is trying to identify important websites. And how this is done is actually by transitive importance. So how can a page be important? It can either be important because a lot of pages are linking to it. So if I'm in the web, I actually want a lot of websites referring to myself. So this is, for example, here's this blue node. This is why it's so big, because it has a lot of incoming links from like many unimportant sites, but still there's many links coming into like this big node here. The other thing is actually if I get links from very important sites itself. So for example, imagine google.com would link to me, or Microsoft.com. This is a very important site by itself. So for example, this red node up here just has like one incoming link, but this is from a very important site. So this by transitive importance or transitive centrality would make this node important as well. And as said, this was kind of like the founding idea, this founding paper, which Google used to build up their search engine. They by now switched a little away from that, but still it's kind of this myth around that. And yeah, if we view that differently, so basically like the same bubbly graph here, we can see here the weight is basically the importance, and then we see like who's linking to whom and how that actually transfers in the graph. And the interesting perspective in how we can view this algorithm is how likely, if a random surfer, a random like web server, how likely will he end up at our page? So he's just going to go to a random page, click on a link, and keep on clicking links until he's like done with a certain probability. He, for example, starts here, clicks here, and then he stops. So overall, it's like the stochastic thing. How likely is a random walker going to end up here? Or similar, coming to same result, is iteratively distributing the rank to neighbor nodes. So basically, every node is sharing its importance with its neighbor nodes, and you do that iteration over iteration until it actually stabilizes. So here, if we look at that, so while the error is is greater than epsilon, so while the nodes are actually changing, we keep doing that. And for all the nodes in our graph, we basically send an update to our neighboring nodes. And often this is implemented by Pregel. So Pregel is a system for a large scale graph processing. And for that to keep in mind, so what made Pregel so prominent or famous, why so many people use it, is because it actually allows you to distribute this graph operation across multiple nodes. So a lot of the other graph, like imagine you're Google and you want to compute that for the entire web. You cannot do that on a single machine. You actually need to scale that out to a large set of different machines. And this is where Pregel actually helps spreading out this work across different worker nodes. And they do that by having different super steps with a barrier where they then start communicating and syncing. And this removes the need for like global locking where everyone would write into like one data structure, and allows to run the individual super steps independently. So each worker can do the work independently, and just at the barrier, they actually have to wait for each other. Let's see one example of how that can work. With a simplified example, we have here our graph. And we want to find the maximum value in this entire graph. So what is the maximum node value? So how can we do that? So at the beginning, all green nodes, they're active nodes, and we have like input queue where all the messages are being stored. In the first step, each node is sending its own value to all neighboring nodes. So for example, 6 is sending its value to 3, to 1, because those are the edges. 3 is sending it here, 2 is sending it here and here. And then we have those values in our input queue. Each node is comparing that. Is my own value or is this value bigger? And updates if needed. And if there are no updates, if I'm not changing my own value, I actually know I can go into the halted state, because I would just send the same update as in the step before, so nothing would change. And then here, for example, for this node, it changed. So in the next iteration, it's going to send a 6 down here. For this node, it's changed. So it will send a 6 update here, because this is a new value. And then in the next iteration, same as before, only this node is going to change, still sends the updates because it changed. But after that, actually all nodes are halted, and thereby we are done. And would terminate the algorithm. So it's basically the step of like computation, send, computation, send. And this basically makes up the super steps on the page before. Where do we have it here? This is one super step: compare, send, compare, send. And obviously it will get more complex in more complex scenarios. Pregel is supported by ArangoDB for a long time. So we have a large number of different algorithms like PageRank, seeded PageRank, single source shortest path, different connected component detection mechanisms, vertex centrality. Oh, this is still interesting. Hits, line rank, label propagation we talked about earlier, also for community detection, already available in there. And in addition, we have a new feature which currently is like experimental. It's called Custom Pregel, which actually has its own webinar, allowing you to write your own Pregel jobs on the fly to be executed across the cluster. And in the end, it's actually very easy to run your Pregel jobs. Here, this is one of the examples, which, for example, is from like the Python Arango driver supported better here. This is why in this example, we use a Python Arango driver. It basically, what you specify is which graph should it run, which algorithm do you want to use, the maximum super steps, how many threads, we can optimize with async, and like where should the results be written. Last is like the algorithms parameter, like where should be our threshold for change, where we want to stop. So this is as easy as you can run a Pregel job in ArangoDB. And there's actually like a full tutorial available for community detection here. So if you're interested in community detection, there's by Stanford University, there's the POCAC social network data available. And what I just need to paste the links there. I actually did all the pre-processing steps here for you. And we'll paste that into the notebook as well. So you can just download an ArangoDB dump and don't have to do those pre-steps here. Okay, that's Pregel. And I think that also in terms of time brings us to the end of this webinar. Sorry for kind of like rushing through a bit at the end. This was still like a lot of content, and we just guess people had to drop out also in terms of time. But thanks so much for taking the time, and feel free to ask more questions in the chat. We'll still be around and try to answer as many of them as possible. Otherwise, here are some more resources. Get started. There's also a graph course together with Chris. Otherwise, feel free to play with those notebooks. Just keep in mind the instances you create. The tutorial instance, they will be auto-deleted after 4 hours. So don't store any data you really want persistent in there. For that, rather go to like either Docker pull ArangoDB or leverage our managed service, which you can also try for free. So, Chris, are there any more questions which we should answer?
No, I think we got all of the questions. Just going to say, definitely, yeah, make sure you check out those repositories. Wanted to mention again, if you are interested in the JavaScript side of things, checking out the repo ArangoBnB for our Airbnb clone. If you're interested in that, and yeah, check out some of the guides that are available just through Oasis even. There's some really easy ways to start with some of the questions that had been asked about some of the different use cases. We have some good examples there as well.
Yeah, just
and also share any notebooks.
The link to the driver page, which includes the .NET driver. And yes, this is being recorded. If you really want access to like the full slide deck, this, as said, will come up with part 2 in a webinar as well. But I'm also happy to share that, and it's also being covered from some different angle in the O'Reilly course. So if you actually have an O'Reilly subscription, search for graph-powered machine learning. I can also paste the link here. I think this is the first iteration, but if you just Google for that on the O'Reilly page, there is a second iteration of this webinar of this course, and this is like a 4-hour version where, as you can imagine, we have some more time to go in some more details of this. And if you have an O'Reilly membership, this should be included in your membership. Otherwise, there are also free trials to check things out. The next iteration, I believe, is going to be on March 9th. Okay, thanks very much. And if there are any follow-up questions, we're available on Slack, Twitter, email. Chris, any other media you're on?
Nope. Yeah, Slack is definitely a good way to get a hold of me. I'm chris.arangodb on the community Slack. So definitely let me know, or you can email me, Christopher@arangodb, or just the learn@arangodb.com is always a good way to get a hold of us for any learn-related content.
I'm Jörg. Just usually people can't pronounce the name, but it's very easy to Google, so I'm pretty sure you can find me. And yes, thanks for all your great questions. I really enjoyed this. This almost reminded me of like non-virtual webinars where you had interaction with people. So thanks so much for contributing and participating. Thanks a lot.
Thanks.